Here we're going to be talking about the real number system and how to do some practice problems before we get into this using these videos. Everything I say, everything I write is important. I want you to be listening and writing everything that I write down. If I write something down, you should be writing it down too. If I say it and you think it's important, you could also write that down. You need to be listening to these and focusing on what I'm saying and writing, and if there's anything that you don't understand, stop us at that moment and ask us for an explanation. Most of the time we're going to use these videos during class, so you'll have teachers around where you can actually get help. You need to use them. So on this first example, we're trying to place these numbers into this diagram, into the real number system where they're supposed to go. It's important that we simplify each of these expressions before we decide to place it. That looks like a fraction, so you might think it's rational, but actually it's going to simplify to a much simpler number. You have to decide what that number is in its simplest form before placing it in a subset. This word, numbers, because that circle contained in that. Looking for the best subset, the best small group that you can fit. For negative 11.2, we see that that has a decimal part. 11.2, you might see that it's a negative number, so you might be thinking that has to be an integer. But since we have a decimal piece, that 0.2 part, that is not a decimal, or sorry, that is not an integer, it's not a whole number, or it's opposite. Down in the first column, 18 number, it's positive, that's a natural number, it's one of the counting numbers. When you start counting, you'd say 1, 2, 3, 4, you'd eventually get up to 18, that's a counting number. Actually, let's just do it by this. Let's pick out all the natural numbers. I know pi is not going to be 1. I know 4 divided by 5 is not a whole number. 15.0, that's really just the number 15. That actually doesn't have a decimal part. Even though there is a decimal point, there's no part that's actually a decimal. There's no leftover remainder part. It's just negative 36 is a negative number. Negative square root of 200, also a negative number. 0, that is not a positive number. I'm going to change right away. It's 450%. Really what percent means. That by 100, 4.5. So that's also a decimal. It's not going to fit into the natural numbers. So I've gotten all of my natural numbers. The only whole number that can possibly go in here is 0, so I'm going to put 0 in there. There's nothing else that's a whole number, but not natural. This is the only thing that's actually going to go into that group. It's not the only whole number. Actually, 18 is also a whole number. Got that one also, got this one, got this one. Let's just take care of the ones with pi, because that is the easiest one to recognize. Anything with pi is a decimal that goes on forever and doesn't repeat. That has to be irrational. Going on forever, not repeating the same number over and over, that's still irrational. It doesn't matter if we multiply by 2, it's going to stay irrational. All right, 4 divided by 5 is 0.8. That's a decimal that stops. It's also a fraction, so we know that's fraction. Negative 36.0 is kind of like the 15.0. That 0.0 really doesn't mean anything. It's just negative 36. That's a negative whole number. So that is a negative square root of 200. We do the square root of 200, and then you change that into a negative. That's about negative 14.14 going on forever. It's not repeating 1414 over and over. It's just repeating random numbers over and over. Anytime you take the square root of something that's not a perfect square, you're going to get an irrational. Square root of 200 is not a nice number. The decimal 0.89582 goes on for a while, but it does stop. That's going to be rational. It's a decimal that stops. And negative 40.5, kind of the same thing. 450% is a decimal that stops. On the next examples, we're just trying to decide if it's rational. So there's going to be an operation happening. It's either multiplication, division, subtraction, or addition. And something's happening in between these two numbers. We just have to decide, is there an irrational number in there? It's going to stay. These are two fractions. They have 1/7 and 1/3. Doesn't matter what that decimal ends up being. I know that fractions are rational. If I multiply two fractions, it's still going to be rational. That is, actually does repeat. And it can be written as a fraction. Really, it can just be written as 1/21, so it has to be a fraction. Weird example, because we actually do have a fraction. But an irrational number in there. 7 is not a perfect square. I know it's going to be irrational. I do the square root of 7, it's going to be a decimal. I divide it by 10, it's still a decimal that goes on forever, doesn't repeat, that's irrational. It's going to be a little bit of a weird decimal, but it actually repeats. I think it's the same 6 numbers over and over. And again, it's just a fraction with I have 14, that's rational. I have a decimal that goes on forever. Not the same number over and over. That's 6, then 5, then 4, then 0. It's different numbers. I'm going to end up adding 5 to this, but if that doesn't change it, I still have an irrational number, plus 5. It's the square root of 45. That's not a perfect square. I can immediately rule that out. Doesn't matter if I times it by 7. I'm going to mark that as irrational right away. Doesn't matter if I multiply times 5 and then subtract 8. It's still irrational. This one is a repeating decimal. Going on forever. It's not repeating 1, 4, 1, 4 over and over. It's just repeating random numbers over and over. Anytime you take the square root of something that's not a perfect square, you're going to get an irrational. Square root of 200 is not a nice number. The decimal 0.89582 goes on for a while, but it does stop. That's going to be rational. It's decimal that stops. And negative 40.5, kind of the same thing. 450% is a decimal that stops. On the next examples, we're just trying to decide if it's rational. So there's going to be an operation happening. It's either multiplication, division, subtraction, or addition. And something's happening in between these two numbers. We just have to decide, is there an irrational number in there? It's going to stay there. These are two fractions. I have 1/7 and 1/3. Doesn't matter what that decimal ends up being. I know that fractions are rational. If I multiply two fractions, it's still going to be rational. That is, actually does repeat. And it can be written as a fraction. Really, it can just be written as 1/21, so it has to be a fraction. Weird example, because we actually do have a fraction. But the irrational number in there, 7, is not a perfect square. I know it's going to be irrational. I do the square root of 7, it's going to be a decimal. I divide it by 10, it's still a decimal that goes on forever, doesn't repeat, that's irrational. It's going to be a little bit of a weird decimal, but it actually repeats. I think it's the same 6 numbers over and over. And again, it's just a fraction with, I have 14, that's rational. I have a decimal that goes on forever. Not the same number over and over. That's 6, then 5, then 4, then 0. It's different numbers. I'm going to end up adding 5 to this, but if that doesn't change it, I still have an irrational number, plus 5. It's the square root of 45. That's not a perfect square. I can immediately rule that out. Doesn't matter if I times it by 7. I'm going to mark that as irrational right away. Doesn't matter if I multiply times 5 and then subtract 8. It's still irrational. This one is a repeating decimal. This part is repeating. So that's rational. Plus a decimal that stops. That's rational. So it ends up as a rational number. It's the exact same thing on the next one, except it's choose that stop. Decimal stops. Decimal stops. Those are both rational. No matter if I multiply them together, it's still. On the last examples, we're trying to write always, sometimes, or never for each of these. I'm going to draw that chart again. I have my integers, then I have my rational numbers. Everything in here, everything in the integer square there, is also contained in the rational number square. For example, negative 3.0, integer, 4.0. That's an integer. Those are both rational numbers. They're decimals that stop. That will always happen. No matter what integer you have, always going to be rational. The opposite is not true. I can think of an example really easily, 1/2. There's sometimes when it happens, though. Examples up here are examples where rational numbers are actually integers. Same thing with the next one. There's some negative numbers that are rational, but some are irrational, like negative 5. 0.5 is rational. That happens sometimes. Some negative numbers that are rational, and some that are not. 0 is always going to be an integer. I'm going to go back up to this chart. 0 in this, which is completely contained in the integer circle. Everything in a smaller circle is contained in the bigger one. So 0, real, it is not natural. It's in the bigger circles, it's not in the smaller one of natural. It is always, whole numbers are always, the last one, irrational numbers are real. Well, all the numbers that we're learning about for now are real. Irrational, rational, they're all real. So